This is a straight line executive black belt supplementary lecture on building predictive models. We're in week 5, and building predictive models is all the rage these days. Statisticians and mathematicians, they have a lot of techniques, but they boil down to really regression. And they're not only that, but those represent a very large class of models that are used today. So we're going to learn, we've already learned simple linear regression, which is fitting a single line, but we're going to take a survey of some of the techniques and tools, and we'll talk just briefly about a couple of the issues that we can run into. They're not so much with modeling, but just some issues that you can run into when you're building models. Okay? We're going to, after we complete this, you'll be able to explain the concept of Occam's razor and its importance in modeling. It's not the only thing that's important, but it is important. Then we're also going to be able to state the cases where some of the following modeling techniques may come into play. Transformations, and then some different techniques: polynomial regression, multiple regression, dummy variables, and design of experiments and time series. I'm not sure we'll cover this. In fact, I know that we won't. We'll cover this later. We just may mention it in passing. This is really, if you're wondering where you can use this in DMAIC, it's usually at least in the analyze phase, but it can be used anywhere, and it's great, great, great general knowledge for business improvement or business analysts. Let's start out with talking about the modeling concepts, issues, and uses. The main reason why you use a model is to reflect reality so you can make certain predictions or measurements. For example, a model airplane is something that you can use to test how wind will bank off of different, like if you want to add an appendage to a wing or something like that, or an antenna, you can build a model airplane. A stock market model may help or may not help you predict the stock market. Or there may be a simulation model for a process that you could use. Often the key thing is that we're trying to predict future performance. We can play out what-if scenarios, and we can tweak the designs if we have a good model to make sure that, to see if we can find better solutions. All right. What we're trying to do here is very similar, but it's more of an inputs-outputs based model. Now, one thing that a lot of people have an issue with is they assume, or they begin to assume, that the model is actually reality. Let's keep in mind that reality is reality. The model only approximates it, and therefore a model is never correct. A model is only useful or not useful. Let's not forget that, okay? Now, models can be extremely useful even though they're not correct. For example, Newton's models for planetary motion still can control satellites, and with great accuracy, and yet we know that they're not right. Einstein proved a lot of what Newton's planetary motion was, planetary models were, strictly speaking, wrong, and yet we still, NASA and other space explorations and other companies and organizations use Newton's laws with great comfort because of their great accuracy. Now, just because a model, even though models are useful, they are sometimes pretty hard to build. And making a good model is an art and a science. It's kind of like being a good cook. You have to decide sort of what goes in a model and what doesn't go in. You have to be able to look for anomalous points. Okay, those are usually outliers, but they can be something different as well. We're going to mostly look at with outliers. Okay, but having said this, models are wonderful because they allow a great amount of scope for creativity. All right, and it can drive what you might be able to do in a business, which is fantastic. Now, when we do build a model, I recommend the following approach. I recommend using simple models before you start using complicated models. There's a number of reasons for that, but one of the reasons is that you build up your knowledge organically, so that when you're using the model, you're using it to its maximum effect, as opposed to the kitchen sink idea of building a model where you throw everything in and then make predictions. It's hard to learn that way. Again, we're never going to build a model just for its own sake. We're going to build it because it's going to be useful. Okay? Again, let's not argue about whether it's right. Of course it's not right. It's a model. Let's talk a little bit about Occam's razor. One of the techniques, or the philosophical techniques that we're going to use as we go through building a model, particularly multiple regressions, and DOE, is a concept of Occam's razor. Occam was a philosopher, a religious philosopher back, I believe, in the 13th century. And basically, he came up with the following model. He said, if two things explain something equally well, we should prefer the simpler of the two explanations. Okay? That goes in models as well. And there's a really important reason for this. Simple models tend to be robust. That means that they're hard to break. Their assumptions work over a wider range of variables, and they're not screwed up by getting future data points the way that real complex models tend to get screwed up. Okay? Here's an example of Occam's razor. Suppose we have the following choice between two of these models. This complicated one on the top, which involves not only one but several terms, 1, 2, 3 terms, or the one on the bottom, which really only involves one. We'll note that the R-squared adjusted, which we've learned last time, R-squared was a key thing that we looked at for the power or predictive power of the model. In both cases, the R-squared adjusteds are almost the same. In this case, we would probably prefer the second one. Why? Because it's a lot simpler. Think about it in terms of having to collect data and then having to operationalize it. Suppose you were predicting staffing levels for nurses in an ER, or suppose you were predicting staffing levels or capacity levels for a call center. Both of those things, if we had one variable to help us predict and it was equally good as having 3, wouldn't we rather just predict with that one? That's the idea. Now, very often it is true that when we have 3 variables, we'll be able to predict even better, but that's not what we're talking about here. Okay, 2 other things that can kind of happen, and they're related. The overfitting issue. Sometimes people throw in so many different variables into a model that they don't realize that they're overfitting. Overfitting can be a real problem. Just don't throw in too many. Don't throw in. Make it a rule to yourself that you're not going to throw in any variable that you don't fully understand and you haven't explored the relationship between the input and the output with that variable. Just make that a rule. You're probably going to be okay there. Second thing is lack of fit. A lot of people will throw a lot of things in a model, but it will still have a very low R-squared. It has a very low R-squared, folks, 10, 20%. Please, 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 you got to take its results with a real large grain of salt when you do that. And then finally, most models, with one exception, that is design of experiment, most models, the regression models that we build, the y equals b0 plus b1x type models, do not assume causality between the x and the y. What does that mean? Just because 2 things are correlated, they coincide with each other, does not mean that they are causal. And we will go over an example of that. Let's in fact do that right away. Correlation doesn't mean causation. If you did think that correlation meant the same thing as causation, you would think that surely this input would cause this output. But now, how do you feel when we put in what this is really about? Suppose we looked at ice cream sales and the number of drowning deaths in an area. Does it seem reasonable that ice cream sales drive drowning deaths? Well, maybe mom was right. Maybe everybody's eating ice cream and then going out there and they're getting a stomach cramp, they're not waiting a full hour, and they're drowning. What's probably happening, what's more likely to happen, is that ice cream sales are correlated with time of the year or temperature outside. When it's hotter outside, there's more ice cream sales, as well as drowning deaths. This often happens when statisticians note that this often happens when you have what's called a lurking variable, a third variable, or even a fourth variable that's behind these things that's also driving this behavior. Now, I want to make sure that you understand this. That doesn't mean that we can't build a model for predicting based on ice cream sales. Okay? We certainly can predict the number of drowning deaths based on ice cream sales if they are correlated, but we can't assume that they're causal. Okay? Causal only comes from the context That's your knowledge. That's the SME's knowledge, or a designed experiment. All right, let's go over some of the techniques. All right, all of these techniques fall under the rubric of least squares models. The form of the equation in each of these cases that we're building looks something like this: y equals b0x plus b0 plus b1x plus b2x plus b3x. We call these terms, and we call the b's coefficients. Let's take a look at transformations first. Suppose we make a model and we make a scatter plot and it looks like this. It's possible that we could certainly fit a line here. I'm just going to draw it in as an eyeball. But what's a problem with that? Well, one of the problems is we've got a ton of data here, but we have very little data here, and we're in no man's land right there. This means that over this area, we've got problems making predictions because we don't have a lot of data to cover ourselves. In fact, we've got, when we do the residual analysis, we'll find that we've got that fan-shaped thing going on there. Erase all the ink on this slide. When we do the residual analysis, we'll find that we have the fan-shaped residuals, the non-constant variance. What can we do? Well, we can take a log or a square root of our original variables, and we'll see how this works. Let me demonstrate how this works. The typical one that we're going to take is a log transformation. And by the way, that is something that we do cover in the section on transformations, how to take a log of a data point. But let me demonstrate what's going on by showing you a different program, and it's a pretty cool program. I've got this set up for looking at exactly the same thing. Here we've got the sales of a company, and we want to predict the assets. And you can see if I put in the regression line, there it is, but I would feel uncomfortable out here. Let's take a look and see what happens when we transform these variables. We'll see that by taking a log of both of these things, that we'll get a much more robust, that is reliable, regression. Here we go. I'm taking the log of assets. There, I took the log of assets, and now I'm taking the log of sales. And look at that. It's much more regular, isn't it? When I add that regression line in, it's a funny regression line, actually. It's got a funny tilt to it. But when I add in that regression line, I should be more comfortable with it. Another thing that happens here is when we do take the logs, we're essentially squashing the scale, and we find that, for example, let's take a look at this right here. You see that you start to see some patterns, like this line right there. Very funny pattern. I'm going to color that something different, maybe. How about green? Green's too close. How about red? Yeah, how about red? So we might want to investigate that. And this does happen to be companies. So let's take a look and see what those are. Mellon Bank. Norwest. That happens to be a bank. National City. Bank. Southeast Banking. Bank. Sovereign Financial. Northstar. California First Bank. Guess what? This happens to be things that had very low sales but high assets, and there are some interesting things that are coming out of this. This was 1986, just before the savings and loan crash. So this has not a lot to do with modeling, but a lot of insight can be gained when you put a proper scale on there. In this case, we took a log. That's very common when you have skewed data, when you have data that are real extreme. Sometimes you take a log, it can really help a lot. Okay, back to the regularly scheduled program. All right, so another type of model that we have is polynomial regression. So sometimes a line doesn't fit so well. My English teacher is getting upset at me for that one. But a curve might fit better. One way to make that curve is that instead of using a line, which would just be b0 plus b1x, we can add other terms of the same variable x. So here's x2, here's x squared, and here's x cubed. So essentially we're taking the same variable and we're squaring it and we're cubing it and we're making that curvature into the model. So that's one thing that we're doing. Another way that we can sometimes improve a model, and we discussed this before, is to add in other variables. So for example, we did before gas mileage as a function of speed. As a function of speed that you drive. If we wanted to improve that, we might also put in the weight of the car or the engine capacity or whatever, the size of the tires. Key thing in multiple regression is that we've got many things that are numbers. Okay? So multiple regression can sometimes make your models a lot better, improve that R squared. Another thing that we can do is sometimes we don't have data, we don't have numbers. Sometimes we have, like, gas mileage might be affected by speed that you drive, but also might be affected by the type of the car. Maybe the types are economy, sports, or SUV, okay, or whatever. There could be others. And so we could break this up by using what's called dummy variables or indicator variables to include categorical variables in our model. Okay, the example that's given here is we might be able to use call type to be able to make an adjustment in if we were figuring out why customers waited a long time in a call center. Maybe call type would help drive that. Okay, finally, we're going to talk about this specifically when we go through some of the week 6 stuff, but designed experiments, actually what's different about designed experiments is that up until now, what happens when we're looking at our X's and our Y's is we're pulling historical data. Because we're pulling historical data, we can have lurking variables in the background changing our relationship between X and Y. But if we proactively adjust X and we watch to see how Y moves, that is, we proactively experiment, we can actually show and demonstrate cause and effect. So that's what's lovely about designed experiments is we can show cause and effect. We can establish cause and effect, which is very, very helpful. Second thing is that if we have multiple X's, we can actually determine if they interact with each other. That might be very helpful in a drug study or in many studies where certain variables interact with each other, certain X variables interact with each other to create a synergistic effect in Y or an anti-synergistic effect in Y. Finally, I would be remiss if I didn't mention that many time series models are out there. Forecasting models that people have for business, these are all regression type models. Now, we're not going to spend a lot of time doing time series. In fact, we're not going to spend any time doing time series. But it's important for you to know that at heart, when the econometrics folks and the economists, the econometricians as they're called these days, when they build their time series models, or the guys in accounting or finance do that, they are regression models. They're regression types of models when they build the forecasting models. All right. Well, we've covered Occam's razor, and we've covered some of the potential issues, mainly the causation. Correlation does not mean causation idea. But we've also covered very briefly what a lot of these techniques are, the transformations, when you might use a polynomial regression, multiple regression, dummy variables, when you might design an experiment, and a time series model. As we go through the course, we'll cover these more in detail. All right, now it's your turn. In your view, what are the key takeaways of this section? What are the questions that you can answer as a result of this, and how can you support business improvement? All right, see you on down the road.